One is valence bond theory, so we'll just take a look at that one first. Let's see if this black is working. So how does valence bond theory describe the bond? And so what we have is we'll have a 1s orbital here on the hydrogen, and this is 1 electron here. And then we'll have another 1s orbital here on hydrogen. We'll make this one spin down. And then we just bring the two atoms together. And so in valence bond theory, we have an overlap of atomic orbitals. This is what creates a bond. So we'll just have the 1s orbital overlapping with a 1s orbital. So we end up with a 1s sigma bond here. A pair of electrons. And so what holds the atoms together is this electron cloud here. In the overlap region, we're going to have a greater density of dots. The electrons themselves aren't clouds. Electrons, they're hard to describe exactly. So the cloud is just giving us a probability distribution. It's like the birds. One time it's here, the next time it's here. It's not like spread out over the entire volume. You pinpoint the position there. Because of the Heisenberg uncertainty principle, we lose some information about the energy of that particular electron. So conceptually, I guess that using the cloud is fine. Just do it, continue that way. But anyway, there's an overlap here, and then we're going to have an increased density of dots, and that's going to pull the two nuclei in towards each other. Here. And so the nuclei are going to be attracted to this greater density of dots between. The nuclei are positive, these are positive 1, and then the electron cloud's negative. So it's electrical attraction that holds the atoms together. It's in valence bond theory. In MO theory, we describe it differently. Just do it again. So they want the energy level diagram here. We're going to do a little bit more than that. Here. First, what we have is we have, rather than overlap, what did I say? Overlap of atomic orbitals, we're going to have LCAO of atomic orbitals. LCAO stands for linear combination of atomic orbitals. Linear combination of atomic orbitals. And when we do that, it makes new orbitals. Called molecular orbitals. Or MOs. We call molecular orbitals MOs and atomic orbitals AOs. And so what is a,
The nucleus were pulled together by electrical attraction? What did you say?
Electrical attraction, that's correct. Positive and negative attraction. the same thing in molecular orbital theory. We look at a bond a little bit differently. And so there's different ways we can represent the orbital like this. You know, 1s orbital here. An alternate way of representing this would be looking at the wave function. If we look at the wave function, we see a wave like this. This would be the psi 1s. When we square that, then we get the probability distribution here. And then another psi 1s. And then when we create the molecule, we're just overlapping those two sides. And then we see in this overlap region, we're going to have increased electron density here. So this is psi 1s, this is psi 1s. So what we're going to do here is we're going to do psi 1s plus and minus a psi 1s. So if we do a psi 1s plus a psi 1s, it's going to look like this. So this is our psi 1s plus psi 1s. And then we end up with something that looks like this. How should I draw this? Just like this, maybe. And this is going to be called the sigma 1s MO. This is not sigma overlap like that. Then we're going to have the psi 1s minus the psi. When we do a minus, it's going to, I'm just going to flip it, so it's going to be flipped over. Now this is like this. So this is positive, and then this is going to be positive, this is going to be negative. And we end up with something like this. In terms of the psi squared. There's going to be a node here. Between the two nuclei. The node is a region of zero amplitude. So probably the better way of representing this is just like this. So I have my 1s orbital here and my 1s orbital here. This is positive amplitude, positive amplitude. This is going to make a new orbital, and this new orbital is called a sigma 1s orbital. However, this one is called a sigma star 1s, and it's called a star because of this. The electron density, when we look at the here, the electron density is going to be in the internuclear region and also outside, but the two nuclei are going to be attracted to one another here because of the negative charge density in this cloud here. Whereas here, when we look at the density here, it's outside the internuclear region primarily. And so what happens is the two nuclei see one another and they're both positively charged, so they repel. So one orbital leads to an attraction, the other leads to a repulsion. And so what the star means is that repels one another, so we call it anti-bonding. This is not conducive to bonding, whereas the sigma 1s, this is conducive to bonding, so we call that a bonding MO. And this is an antibonding MO. And so we make both of those. So if we take two atomic orbitals, we make two molecular orbitals, one bonding and one anti-bonding, always, because we flip the phase. So two atomic orbitals yields two molecular orbitals. One bonding and one anti-bonding. Therefore, the way we describe a bond is a little bit differently. Over here, we describe a bond as having this overlap region being increased electron cloud density, which means an attraction to the overlapped region. Well, the same thing happens here, except now we have these anti-bonding orbitals, so we have to define things a little bit differently. And so for MO theory, we calculate the bond order based on MO. Theory. In the bond order, this is just equal to the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So the way we do this is we draw an MO diagram. This is going to be an MO diagram for the first shell or period. So we have a 1s orbital here on atom A, and then over here on the right, I'll write a 1s orbital for atom B. And then in the center of these two, I'm going to put the molecule AB. When we do this, we can have positive amplitude and positive amplitude. That's going to result in constructive interference, and we form a bonding MO. This bonding MO is called the sigma 1s. And so I'll take a 1s orbital here on atom A and a 1s orbital here on atom B, and I'm going to make a sigma 1s orbital here on the molecule, which is going to be cigar shaped like that. All right, that's going to result in a lower energy because forming bonds releases energy, whereas breaking bonds increases energy. All right, just as high up, energy is conserved. So if we drop down this much for the bonding, we got to rise up this much for the antibonding. So the antibonding is going to be up here, sigma star 1s. And the shape of that orbital is going to look like this. The nuclei here, nucleus here and there, and then the lobes are going to kind of be repelling one another like this. And one characteristic of an antibonding orbital is they have a node. That is a region of zero probability of finding the electron. And so that would be an antibonding orbital here. So in this lab, they're asking for the energy level diagram. The energy level diagram, what that is equal to is the MO diagram. So this is the MO diagram. And so the MO diagram, we could either just show the MOs or we could show the AOs and the MOs. We're going to show the AOs and the MOs. So we're going to draw the MO diagram for hydrogen. So we're going to have one s orbital here on hydrogen. That's going to have one electron here. And then over on the right, we'll throw another 1s orbital for the second hydrogen here. We'll put its spin up because they're separate. We haven't done a linear combination yet. Now we're going to do the LCAO. When we do the LCAO, then we form two new orbitals. One is going to drop down here. This is going to be the sigma 1s orbital. And then the other is going to rise up here by the same amount. This is going to be the sigma star 1s here. And so this is the MO diagram. Now we need to fill the MO diagram. So technically just the center part's the MO diagram here. And so sometimes people won't show the original AOs. This is the AO, this is the AO, this is the MO here. But a lot of times people will show the AOs and the MOs together. Oops, I forgot to turn this here. What I was talking about earlier. Going back here. So now we fill the MO diagram. The Pauli exclusion principle holds for MO diagrams. So fill according to the normal rules. Fill MOs using the same rules. As AOs. So we fill the lowest energy orbitals first off bow. The orbitals hold a max of 2 electrons. That's Pauli exclusion principle. Although we're not going to do the quantum numbers for these. That's for AOs. So what we're going to do is we're going to take 1 electron from 1 hydrogen and the second electron. They have to be anti-parallel, and they have to have opposing spin according to Pauli. And we have 2 electrons in the sigma 1s. 2 electrons in the sigma 1s means that, we're going to have the 2 electrons here, which is going to create the bonding interaction here because the cloud density is here. Whereas the anti-bonding orbital is empty. It's empty. It's fine. So there are 2 things that we get from this. Number 1, we want the bond order. The bond order is equal to the number of bonding electrons, 2, minus the number of anti-bonding electrons, 0, divided by 2. The bond order is 1. So what we say is that there's a hydrogen-hydrogen single bond. And the second thing is we go for the magnetic properties. In terms of magnetic properties, we have 2 big ones that we worry about. The 2 big ones that we worry about are diamagnetic and paramagnetic. Diamagnetic means all paired. Paramagnetic means unpaired, at least one unpaired. This one's diamagnetic. So we have a bond order 1 and it's diamagnetic. That doesn't seem like a lot of information, but MO theory gives much more. MO theory gives the excited states, you know, the higher energy orbitals here that one could predict. Well, valence bond doesn't do this. You know, valence bond, we just have the overlap of the atomic orbitals, but what are the higher energy excited states? It doesn't tell us. MO tells us much more information than what valence bond does. The disadvantage of MO is it gets more complicated. As we get higher. So here we are with the information that we're going to get. Number of bonding electrons, 2. Number of anti-bonding electrons, 0. Bond order, 1. Diamagnetic. That's it. Not a lot of information we're getting. In order to do this properly, we'd have to do some quantum mechanical calculations, which if we still had Spartan software, we would be able to do easily. We could go into the computer lab and do this, but unfortunately, that wasn't funded, so we're not going to do that. We're going to skip the computer lab. Let's look at H2 plus. Let me do this on the side here. Let's do H2 plus using valence bond theory. If we do this, this is like taking a hydrogen molecule and knocking an electron off, which you can do. Ionize a hydrogen molecule. Move this over. So in terms of valence bond, we can take an H plus cation, which is going to be empty, and then a hydrogen atom, which is going to have 1 electron in here, 1 atom. And then we bring them together. We bring them together, we form the overlap here. And we end up with H2 plus. H2 plus is should be okay in valence bond theory, except it's going to have half the electron cloud density in here. If it has half the electron cloud density, is it going to be as strong of a bond? No, it's going to be a weaker bond. And so we expect H2 plus to form here. It's just going to have a weak bond. You'd think. That's valence bond theory. Let's take a look at MO theory next. Now, this is still first so first shell. So we have a hydrogen plus, meaning this 1s orbital is empty, and then we have a hydrogen normal, it's going to have 1 electron. And then what we're going to do is we're going to form our bonding MO, which just people memorize as sigma 1s, and our anti-bonding MO, which is going to be a sigma star 1s. This is going to form H2 plus here. And so essentially it's taking an H plus and an H and combining them together. The LCA is still going to happen regardless because we have the 1s orbitals. But now we only have 1 electron in here. It could be either spin up or spin down. And so what we want to do is we want to calculate the bond order. So how many bonding electrons do you count? 1. How many anti-bonding electrons? 0 divided by 2. The bond order is 1/2. This is a weaker bond than you'd expect. For a bond order of 1 would be a stronger bond. This one has an unpaired electron, so we call it paramagnetic. Now, paramagnetic materials will be attracted to magnets, like water. Water is paramagnetic. Is water? No, water is not paramagnetic. Water has all paired electrons, however, it's attracted to magnets because of its dipole. But these will be strongly attracted to magnets. If you knock an electron off a hydrogen molecule, these hydrogen will be attracted magnets. And what they try to do sometimes is they try to confine them in a magnetic vessel. You know, it doesn't have walls; it just has magnetic walls. You know, you confine it. They're trying to do this for fusion reactions. Fusion reactions, like they're trying to do nuclear fusion, like the sun on Earth. And there are a whole bunch of startups right now trying to do this. Except the temperatures that are required are so hot they vaporize metals, so you can't use metal container. You can't use a lot of other kinds of containers too because of temperatures. So they try to confine it using magnetic and electric fields. And so it's important. If it's diamagnetic, you aren't going to confine it in a magnetic field. All right, so far so good, I think. Let's go to He2. So for comparison, we want to do He2 using valence bond theory. And so if we do helium, which is going to have a 1s, it's going to be filled. And then we throw in another helium in there, and then try to bond these together using valence bond theory. So if we try to bond these together, what's going to result is we're going to get like this, a 1s sigma bond, but there's 2 electrons here, 2 electrons here. Is it going to happen? No, it's too many electrons. Because in this overlap region, I mean, we have to double count the electrons. So that's 4 electrons in one orbital potentially. It's not going to work. And so no bond should form here. And then we go to helium. So we need to do the first period or the first shell MO diagram. The first period or first shell MO diagram, people just memorize. 1s, 1s, going to sigma 1s, sigma star 1s. Okay, and then we have a helium over here. Helium has 2 electrons in the 1s. And we have a helium over here with 2 electrons in the 1s. And then we try to make the He2 molecule. And we fill these. I have a total of 4 electrons to fill my MOs here. So the first 2 will go in the sigma 1s, and the next 2 will go in the sigma star 1s. So that takes care of the 4 valence electrons here. When I calculate my bond order, how many bonding electrons do I have? 2. How many anti-bonding electrons? 2. Divided by 2 is 0. A bond order of 0 means it doesn't exist. There's no bond. No bond. And so it doesn't make sense to say whether it's paramagnetic. It would be diamagnetic if it would exist, but it doesn't exist. And so He2 doesn't. No bond. Yes.
So, they said you're bond order, so say like no bond.
Zero. Bond order is zero. No bond.
And you the empty for the
Diamagnetic and paramagnetic only works for if it exists. So it doesn't exist. So therefore, there's no magnetic properties to measure for it. So just say not applicable, Na. So next we have He2 with a positive charge. So what would that be? Oops. An He2 with a positive charge means, let's do this. Using valence bond theory. Using valence bond theory, I'm going to have a 1s orbital here. This is helium. I'm going to make it a positive helium. A positive helium has lost one electron, so we'll just have one electron there. And then I'll have a normal helium over here with its 2 electrons. And so, throw it over here. And then let's form a 1s sigma bond. When we form a 1s sigma bond, how many electrons am I going to have? I'm going to have 1, 2, 3. Can I have a sigma bond with 3 electrons like this? No, I can't, because those 3 electrons could potentially be in this 1s or they could be in that 1s. I can't have 3 electrons in one 1s orbital. That would be a violation of the Pauli exclusion principle. And so He2 plus does not exist. We're not going to have 3 electrons here. What does MO say? So far, MO and valence bond are quite similar. When you look at a 1s sigma bond, doesn't that look like a sigma 1s orbital? Yeah, when I look at a 1s sigma bond, it looks similar to a sigma 1s. They're similar. Well, anyway, I'm back here to the first shell. So it's 1s. What does it make? It makes a sigma 1s and a sigma star 1s. Now these are not sigma bonds and pi bonds. These are sigma MOs. And so sometimes people get confused. The difference between those. So over here I'm going to put helium missing 1 electron. That's 1. And then over here I'll just have a normal helium with both its electrons. So when we do this, we fill these. So the sigma 1s will be maxed out at 2 electrons, and the 3rd electron will have to go up here into the antibonding. So that takes care of the 3 electrons in the 3 valence electrons in He2+. The valence electrons are the same as the total electrons. Let's calculate the bond order for this. How many bonding electrons? Antibonding? It gives us a bond order 1/2. Uh-huh.
So even though the bond order is not 0 and it violates the Pauli exclusion.
This doesn't violate the Pauli exclusion. We are not putting 3, this is not a violation. We're not putting 3 electrons into 1 orbital. Over here, when we overlap these, that means these 3 electrons occupy both or either. And so these 3 electrons could be in this 1s, or these 3 electrons could be in that 1s, or they could be spread apart, like 2 and 1. But the problem is that we can't have 3 electrons in 1 orbital. Whereas this is totally different. we're not putting 3 electrons in one orbital. We're putting 2 electrons in the sigma 1s and 1 electron in the sigma star 1s, which is a higher energy orbital. Now, there's no higher energy orbital like with the 3rd electron here, you know, in our analysis of valence bond theory.
Okay, so valence bond theory analysis doesn't work for this example, but the MO energy diagram.
Right, so valence bond predicts that He2 plus does not exist. The valence bond predicts He2 plus to not exist. MO predicts it exists, it just has a weak bond. MO predicts He2 plus exists. So, which is it? Does it exist or does it not exist? And MO is correct. He2 with a positive charge does exist. So that means valence bond is wrong. If valence bond is wrong, like the Bohr model, remember the Bohr model, Bohr theory? That was all wrong. Did we spend any time working? Some books do, but I didn't spend any time doing Bohr because it's wrong. We did quantum. The same thing here. Should we have even bothered with valence bond? Why even teach valence bond theory if it's wrong? And the reason is because sometimes it's not so wrong and sometimes it's very wrong. And the times it's very wrong, we can make a note of, you know, for exotic species like this and one other species that we'll talk about. But the advantage of doing valence bond is when we look at the electron cloud, it's similar. You know, so for example, the sigma 1s is similar to a 1s sigma orbital from the overlap. And so what we have to do is we have to imagine the electron cloud density a bit different. And just in certain cases, it's quite a bit different. And so in valence bond, we try to cram in 3 electrons in here, in the electron cloud. So we're trying to cram in these 3 electrons in here. Well, that turns out not to be correct. And so when we look at MO, what we have is we have 2 electrons in the sigma 1s. Let's throw those in here. And that's going to hold these together. Like that. But we have a higher energy orbital. It's called the sigma star 1s. And we have 1 electron in here, in the sigma star 1s. Either in this left lobe or in the right lobe. We'll just draw the cloud like this. And that's going to lead to an antibonding interaction. But since we have more density in the bonding than the antibonding, we have a net bonding interaction. If we had equal amounts of antibonding and bonding, then they would cancel each other out. And so, the primary advantage of retaining valence bond is, you know, it's close, but it can be wrong sometimes. So anyway, this would be paramagnetic here because of the 1 unpaired electron there. The more unpaired electrons, the more paramagnetic it is, the more strongly it is attracted to magnets. So this is a success story for MO. Li2 plus comes next. And so we're going to work on the next shell. So when we get to the second shell, like lithium, we're going to ignore the core, the 1s core. We're just going to go to the second shell. The second shell, atom A is going to have a 2s followed by 3 2p's. I'm going to draw them like this. Actually, how should I draw them? This. Now the 2s on atom B, we'll have a 2s here, and then 2p here. What happens here is that the 2s are like the 1s, so we'll have a 2s combined to make a sigma 2s. A sigma 2s is just a large version of the sigma 1s, except we're going to have a node in here, internal. And then we're going to have a sigma star 2s. Which will be like the sigma star 1s, except there's going to be another node in there. Now for the 2p's, we have 2 ways that we can do LCAO. We can do it like this, head on. Like here, positive, positive, negative, negative, like that. This is going to create the bonding MO. The bonding MO is going to look like this. Something like that. Where we get the positive, positive, constructively interfering. If we flip it, so we put the negative amplitude here and positive amplitude there, then the positive and negative amplitude cancel. We end up with this. This would be the antibonding. So we call this the sigma 2p, and we call this one the sigma star 2p. So that's going to be here. I should have made this a little bit bigger. Sigma 2p, and then up here, about the same amount, sigma star 2p. And those would be the orbitals there. We can also have the, these are the px's. So this is a px, let's say this is a px here on A and B. We could have a pz or py. Let's take a look at the py. If we look at the py and another py here, we'll put them in sync with the amplitude here. And that's going to make an orbital that looks like this. If we look at the internuclear axis here, this is the internuclear axis here. There's a node, because there's a node here and there's a node here. And so these two positives add up and these two negatives add up constructively. And so we call this a pi 2p orbital because the electron cloud density is here outside of the internuclear axis, whereas this is a sigma molecular orbital because the electron cloud is within the internuclear axis here. If we flip the amplitude here, so we'll just go like that, we generate this orbital here. Where it looks like the p orbital lobes are repelling one another, and there's a node here. Node. This is called the pi star 2p. And so this would be the py. The pz would stick out of the board, but they would be degenerate, energetically degenerate. And so the py and the pz's are going to be here. So I'm going to write two lines here, and these are going to be my pi 2p's, and then up here will be my pi star 2p's. Now sigmas are typically better bonds, and so that's why the sigma 2p is lower in energy here than the pi's. When we get this direct, let's see if I forgot to rotate this. Thing about not having the tracker working. So you can tell that, you know, the sigma is going to be better because the two nuclei are going to be attracted to this cloud region directly in between here, whereas the pi aren't going to be as good. And so we expect the sigma orbitals to yield stronger bonding interactions because of the attraction directly towards each other here. Whereas the pi ones are going to be attracted up here and down here. But, you know, there's going to be a net attraction towards each other. It's just not as favorable. And therefore, the sigma 2p's are more favorable molecular orbitals than the pi 2p's here. And likewise, the pi stars aren't as bad as the sigma star here. The sigma star is worse here than the pi star here. The other way we remember this is, you know, if we drop down low, then we have to go up high. So that gives us our orbitals. And so this is the MO diagram in the center for AB. Now, there's one other thing that happens. And one other thing that happens is this. There are two second period MO diagrams. And so I need to talk about the two. So let's try to stack the MOs one on top of each other and see what it looks like after I draw the second. So we have our normal second shell MO diagram like this. And I'm just going to draw the MOs. So we start off with the sigma 2s followed by what? Sigma star 2s followed by sigma 2p followed by pi 2p, pi star 2p, sigma star 2p. That's good. So this is our normal MO diagram here. We have an abnormal MO diagram. Nobody calls it abnormal though, but it's abnormal because what it looks like is this. It starts off normal, sigma 2s. And then sigma star 2s. But the abnormal part comes here. Rather than sigma 2p, we see the pi 2p's. And then the sigma 2p comes next. And then it goes back to normal with the pi star 2p's. And then the sigma star 2p. So what's abnormal about this one? What's abnormal about this one is the position of the sigma 2p. Why here? It's supposed to be here. And then it got bounced up here.
I don't know why, but there's something about being in lithium through nitrogen that you have to do the abnormal MO, right?
Right.
Right.
Yeah. Right. The abnormal, that's correct. From lithium to nitrogen, we use the abnormal diagram. And then for oxygen, fluorine, and neon, we use the normal diagram. And so the reason is this. The Z effective is higher. Here. Over here, Z effective is lower. So, well, let's go back to the normal diagram and we look at a higher Z effective. And what we're going to do is we're going to look at the sigma 2s and the sigma 2p. So when the Z effective is higher, the sigma 2s is smaller. Than the sigma 2p. So when I look at the electron cloud, here on the sigma 2s, the electrons are mainly concentrated, within the 95% boundary here. And then I look at the sigma 2p, the electron cloud is mainly concentrated within the 95% boundary here, but they can avoid one another. That is, the sigma 2p can avoid being around the sigma 2s, and the sigma 2s can kind of avoid being around the sigma 2p because there's room. So this is with a large Z effective. With a small Z effective, it doesn't contract the orbitals as much. And so with a smaller Z effective, the orbitals are bigger, like this. And so the sigma 2s is bigger, like that. And the sigma 2p is bigger, but the S is more penetrating than the P. And so we end up with something like this, where the sigma 2p doesn't contract as much because P orbitals are less penetrating than S orbitals. And so what happens here is that the 2s cloud in the 2p cloud are occupying the same volume. And we get repulsion. So this bump up in energy is due to repulsions with the sigma 2s. And so it gets bumped up because it's being repelled, the sigma 2p electrons. The sigma 2s again are more penetrating. And so the sigma 2p are going to get bumped up in energy, which kind of screws up the nice symmetry that we had with our chart. We had a better symmetry over here than here. And so what that means is we have to memorize two charts or remember these two charts. And so let's take a look at Li2 plus first. So it's kind of weird to think about that the smaller Z effective, the greater the repulsion. And it screws up the chart, or not the chart, but the diagram. And so lithium, so we're going to use the lithium through nitrogen diagram, which is the screwed up diagram. And so the screwed up diagram is going to go sigma 2s to sigma star 2s. And then we have the pi 2p's followed by the sigma 2p, followed by the pi star 2p, followed by the sigma star 2p. And so we need to use this diagram here. All right, for lithium, we only have the 2s that we have to worry about. And so let's put one lithium over here, one lithium over here. This is going to be a 2s orbital and a 2s orbital, atomic orbitals. And so this is going to make the MOs here. Now, one of these lithiums I'm going to make positive, and the other lithium I'm going to just have normal. So how many valence electrons does lithium have? Lithium only has one valence electron, so we'll throw it over here. I didn't have to draw the whole diagram. I guess I could have just drawn this first part, but it's all right. And therefore, Li2 plus will have one electron in the sigma 2s. Which means, what for its bond order? Yeah, it's going to be 1 minus 0 divided by 2, which is a bond order of 1/2. So it exists. It should exist. And is it paramagnetic or diamagnetic? It's paramagnetic. So that's it for Li plus. Next, we're doing beryllium-2, Be2. So for beryllium, we'll just do the AO here. It's a 2s valence. How many valence electrons does it have? 2. Both of those are going to go in the 2s. And then we'll have another beryllium here. Be in the 2s. 2. Okay, and then when we do an LCAO, we form one bonding. So this will be the sigma 2s bonding, and one anti-bonding. This will be the sigma star 2s anti-bonding orbital. And then fill the orbitals for Be2. 1, 2, 3, 4. And so we completely fill this. I'm not going to draw, the higher energy ones are going to be empty here. So I'll just draw this here, which gives us a bond order of what? So that's 2 bonding electrons minus 2 anti-bonding electrons divided by 2. It gives us a bond order of 0, which means that Be2 is predicted not to exist. That's correct. No bond. Therefore, Be2 doesn't exist. How about B2? I'm sorry? Okay. Okay. Okay, moving on. Let's try B2 next. So there are 2 approaches you can take. One, you can do the AOs and followed by the MOs, or 2, you could go straight to the MOs. Which one do you want to do? Okay, if we go straight to the MOs, then we do total valence electrons. Is equal to what? Yeah, so boron has 3, and so we got 2 times 3 to give us 6 electrons here. Now, do we use the normal MO or the abnormal MO? We're going to use the abnormal MO. The abnormal MO, do you remember the orbitals? We start off with the sigma 2s, that's normal, followed by the sigma star 2s, that's normal. And then comes the abnormal part. It should be the sigma 2p next, but instead it's the pi 2p's, and there are 2 of them, so we go to the pi 2p's. Now it's followed by the sigma 2p, and then it goes back to normal, which is the pi star 2p's, followed by the sigma star 2p. So if we go straight to the MO, then all we have to do is fill this MO with 6 valence electrons for B2. And so we just fill them from the bottom up. 1, 2, 3, 4. Now we have to follow Hund's rule. We fill degenerate orbitals singly with parallel spin. 2, 4, 5, 6. And so we end up with this. Next, we calculate the bond order. What is the bond order here? How many bonding electrons do I have? Yeah, 4. 2 here and then 2 up here. So that's a total of 4. And anti-bonding electrons? 2. Divided by 2 gives us a bond order of 1. So we expect a single bond here. Is it paramagnetic or diamagnetic? It's paramagnetic. And so this is the way we visualize the bond happening in B2. In B2, I'll have a boron here and another boron here. And so I'm going to have bonding electron cloud density, I'll write in black here. This is in the sigma 2s. And then I have anti-bonding electron density. The anti-bonding electron density cancels out the bonding electron density here. So the bonding electrons are canceled out by the anti-bonding electrons in the sigma star 2s here. And so far I have 0 bond. The bond's going to come in when I look at the next orbitals. What are the next orbitals? The next orbitals are the pi. And so I have 2 pi's. I'll put the py, this is a pi 2 py like this. And so I'll put some electron cloud density here and electron cloud density here. And so I have 2 lobes. This is going to be similar to a pp pi bond. And then I'm going to have attraction here, here, and here, and here. Not as strong as the sigma, but still pretty decent attraction there. And so this is just 1 pi orbital, but actually I only have 1 electron in there, so I shouldn't have done too dense of dots here. And so that's this one here. Let's make that this one here. And then I have another pi here. I'm going to call this the PZ. So this is my 2py. The PZ is going to stick out of the board here. So that's 1 lobe sticking out, and then there's going to be 1 lobe sticking down behind. It's going to have 1 electron in it. And so I'll have some density here too. And that's going to attract it coming out and going in. So I'll draw a wedge coming out here, attract, and the dash going in. And so one of these orbitals is wedged out on the orange, the other. So if I did a side view, I'd just take this and rotate it 90 degrees, and that would paint the orange ones coming above and below the plane where the green ones are, which is superimposed there. And so what I see is I see a net electron cloud density in the bonding region. And so 1 bonding is canceled out by the anti-bonding, but then I'll have some bonding here that's not canceled out. And so that's the bond, B bond. Okay with this?
Is this fine to do instead of drawing the actual diagram? Is this acceptable normally or no?
What is the actual diagram?
Like drawing out the lines and writing like 2s on the sides and filling those, you know what I mean?
Yeah, either way is fine. So we could do it here, like boron as a 2s, 2p, 1.
But you can do it that way, that's fine.
We could do it this way too. Some people prefer to write the atomic orbitals here, so it helps them remember how to do the MOs. Other people prefer not to do the atomic orbitals and go straight to the MOs. You could do it either way. The book will go straight to the MOs. I'm sorry?
What's the orange part that that's the big
The orange part is the other pi. This is the pi 2pz. Is what it is.
On an exam, would we have to draw that? Like, the orbitals?
Possibly. Yeah, actually, yes, you will have to draw it. On the exam, you'll have to draw it to get full credit. I'll show you examples. N2 is a hard one. Take a look at N2. We're just going to go straight to the MO for this. How many valence electrons total? How many? 10? Well, how many valence electrons does nitrogen have? This is one of the things that people screw up the most with the MO diagrams is they miscount the valence electron and they fill the orbitals. The other one is just using the wrong diagram or just not even knowing what the diagram is. Just single N, 5 and then times 2. This is 10 electrons total. For the N2 molecule. These are the valence electrons. The valence electrons is where the bonding happens. This is where the chemistry happens. Not the core electrons. You know, core electrons, the chemistry doesn't have them there. If we're looking at like ionizing things, you know, or electron affinity, you know, like nitrogen. Nitrogen is 5 electrons. So one choice is we could do EA1. Do you recall what EA stands for? EA stands for electron affinity. So if we do electron affinity 1, we get N minus. If we do electron affinity 2, we get N2 minus. If we do electron affinity 3, we get N3 minus. If we do electron affinity 4, we get N4 minus. So normally to put the first electrons exothermic, but to put the second electron on there is typically endothermic. And then the third electron in there is going to be endothermic. What about the fourth electron? Does nitrogen want a fourth electron or does not? It doesn't want the fourth electron. Why? It would have to go in the next shell. Going in the next shell is going to cost you a lot of energy. So it's reasonable to put the first electron, the second electron, the third electron, but to try to put the fourth electron in there, it's going to climb high in energy because this electron is going to go in the next shell. And so this is filling the shell. And then this goes in the next shell, which is going to be unfavorable. Likewise, we can go the opposite way. We could do IE1. IE1 will get us N plus 1. We do IE2. This gives us N2. Then we do IE3. Which gives us N3. IE4, which will give us nitrogen in the plus 4. And then finally IE5, which gives us nitrogen in the plus 5. Nitrogen in the plus 5 oxidation state we know is significant because what's significant about nitrogen in the plus 5 oxidation state? Well, how many electrons does it have to lose? 5 in the valence and then 2 more in the core. So if we lose all 5 valence electrons, then we can start on the core, but there's a problem with the core electrons. The core electrons are much closer to the nucleus, which are going to be much harder to ionize. And so what happens here is this situation here. We start off with nitrogen, and then to ionize the first one's okay. Ionize the second one, that's okay. It's going to cost energy. Ionize the third one, it's going to cost energy. Ionize the fourth, it's going to cost energy. The fifth is going to cost energy. Actually, this should keep going up. The fifth is going to cost energy. But what happens if we try to do IE6? Then we're ionizing not a valence electron, we're ionizing a core electron, and the energy skyrockets way up here. That's because you're trying to ionize a core electron, whereas these are valence electrons. And so typically what happens with IE1 to IE2 is like double the amount of energy, roughly. So if IE1 is like 1,000, IE2 is like 2,000, and then kind of doubles. But when you get to a core, it's like 10 times, 10 times plus the energy. And so when we're thinking about chemistry, we focus usually on the core electron. No, not the core. We don't really do anything with the core because the core electrons are too costly to react. It's not that they can't, it's possible to take core electrons, it's just going to be very unstable. And therefore, chemistry happens with the valence electron. So valence electrons, this is a very basic question, chemistry. How many valence electrons does nitrogen have? You ask a chemist that and they'll know right away, 5 valence electrons, because they're so important in dictating properties. With 5 valence electrons, it can gain 3 or lose. Where does that come from? That comes from the energetics of this. It would be too costly otherwise. And so, 5 valence electrons per nitrogen. We got 2 nitrogens, 2 times 5, that gives us 10 electrons. We can go straight to the MO diagram. We have 2 MOs that we got to worry about. We have the abnormal and the normal. Is this going to be the abnormal one or the normal one? This is going to be the abnormal one. The abnormal one, it starts off normal, sigma 2s, sigma star 2s. And then goes abnormal here because we get the pi 2p's. And then the sigma 2p, which should be lower, is higher, but everything else is normal. The pi star 2p's, and then the sigma star 2p. So the only abnormal thing is the position of the sigma 2p, which would be lower than the pi 2p's. And then we fill it with 10 valence electrons. Nitrogen has 10, so 1, 2, 3, 4, 5, 6. So we fill this according to Hund's rule. Once we fill them singly, then we'll have to pair it. 7, 8, 9, 10. And so we have these orbitals here. And then we look at the bond order. What is the bond order for this? How many bonding electrons? Let's go ahead and do the count. 2, 4, 6, 8. How many antibonding? 2. Divided by 2, which gives us a bond order of 3. So we expect a nitrogen-nitrogen triple bond is what we expect here. Is it paramagnetic or diamagnetic? Diamagnetic. Now, how do we describe the triple bond? There are 2 ways we can describe this triple bond. In terms of valence bond theory, this is one way of describing it. In terms of valence bond theory, what's the hybridization on nitrogen? Okay, that's okay. It's sp hybridized. And so in terms of valence bond, we have sp hybridization on the nitrogens. That means we're going to have one sp orbital here, another sp orbital here. And so we're going to create an sp-sp sigma bond. And it's going to be here. And then we'll have a lone pair out here in the other sp orbital here. This is not 3 electrons in one orbital. This is 2 separate sp orbitals here. This is another sp lone pair. So that's one of the bonds. Now there are 2 more bonds that we got to deal with. One we'll call the py. So we'll take a py here and a py here. And we're going to form a pp pi bond. And so we'll have 1 electron here, 1 electron here. That's going to create this cloud density here and here. I should. And so far we have this sigma electron density here and the sigma bond, and then the pi here, which is going to be above and below the internuclear axis here and that. And then we also have the pz orbitals. The pz orbitals are going to stick straight out here and in. So this will be a pz. One lobe goes out, the other lobe goes straight in on the other side. Straight out and straight in. So that's my other pz here. So I have 1 electron here in this pz, 1 electron here in this pz. And then I'm going to have overlap here. So I'm going to have cloud coming out and then cloud going in the board. That would be my triple bond, the black, the purple, and the orange, creating the triple bond. And so this would be my other pp pi bond. How does that compare to MO? Let's take a look at the MO next. So I have my sigma 2s here. And I have 2 electrons in that. So I got this. However, that sigma 2s is going to be canceled by my sigma star 2s. And so this bonding essentially is going to be canceled by this anti-bonding. And so I'm pretty much at 0 now. No bonding interaction. Then I go to the pi 2p's. I have the pi 2py and the pi 2pz. So the pi 2py I'll write up here and down here. So this will be my pi 2py. And then I have 2 electrons in these here. So it's bonding. And then I have my sigma 2p. Well, the sigma 2p and the sigma 2s in the abnormal are comparable in size. That's what leads to the extra repulsion. So this will be the sigma 2p, and the inner one will be the sigma 2s. And they kind of overlap, they're in the same region. However, the sigma 2s got canceled out because of the antibonding. The sigma 2p aren't, they're still there. Oops, I forgot the other pi. The other pi is going to stick out. And so this is the pi 2py. I have to write the pi 2pz. Let's put it in here. This comes out of the board, and then one lobe goes in. So it looks just like the py, except it's just, rather than a side view, it's looking at a top view. And then we got the electron cloud density from that. So when you look at the electron cloud density of valence bond versus electron cloud density of MO, is there a huge difference? Take a look at how the dots are. You know, we got these orange dots above and below. Well, we got the orange dots above and below. We got these purple dots here above the plane, the internuclear below. Then we got the purple dots here, and then we got the black dots. Is there a huge difference in the electron cloud distribution? No. And so this is why a lot of people still teach valence bond, because there's not a huge difference here. All the electrons are paired here. Do you see that? All the electrons are paired there. Except, do you see the lone pair out here and here in the MO? No. And so that there is a difference. There's no lone pair stuck out here and lone pair stuck out there. You know, we have the antibonding, yes, but that's one pair. And so it is a little bit different, but kind of the same for the most part. Would you agree? If we do N2 plus, if we do N2 plus, we go from 10 electrons to 9 electrons. Which electron are we going to lose? Are we going to lose a bonding electron or an anti-bonding electron? We're going to lose a bonding electron. So in N2 plus, we just have 9 electrons to fill. Therefore, this orbital is only going to have 1 rather than 2. And therefore, it's going to be paramagnetic instead of diamagnetic. And its bond order is going to be what? Two and a half. And so it's going to have a weaker bond. That is, we're going to have one of the sigma 2p is going to have less electron cloud density in here. It's going to weaken the bond. Does that make sense? Okay. All right, so this is what I want you to do right now. I want you to do oxygen. Oxygen turns out to be the major failure in valence bond. Valence bond predicts the wrong thing. And so oxygen cannot be described reasonably with valence bond theory, meaning you can only use MO theory to describe oxygen, the bonding in oxygen. N2 plus is paramagnetic. N2 is diamagnetic. N2 plus is 9 electrons, so you just do the same thing. All right, so why don't you try oxygen here?